Welcome to a new test and teardown video. Today we're going to play with a Philips oscilloscope called PM3311. It's a full digital oscilloscope and its analog bandwidth is 60 megahertz. It's digital storage, as you can see, and this model is a 125 megahertz sample rate. So here I can turn on and off the different memories, and this is my live input. There's quite a lot of funny features with this digital scope, and other digital scopes about this era, they started to add text readouts and everything inside the screen. Well, this one is doing something different. They're reading out stuff on really nice little LED displays here, and those are these alphanumeric, super nice displays, by the way. And they read out the different settings of everything. Of course, you're supposed to use the different memories and all that kind of stuff this scope got. So what they have done is they have limited the input range of each of the channels to this tiny little area up here. So let me try and see. So this is only the two and a half divisions you get of input signal. That is up here. And this, of course, applies to both of them. So when you have a signal that is over the limit, then it starts to blink. I don't know if that is easy to see. So that piece of the signal that is over limit is just blinking to tell you that you need to move the input like that. So here's the funny thing. Look what I just did. I cranked up the frequency to just to 20 kilohertz instead of 2 kilohertz. So by going faster or slower here, this scope of course tricked me, because it is a full digital scope. It stores everything into memory and then it plays back stuff slowly to the CRT. So that is why no matter how fast or slow I go with my time base, the picture still blinks at the same slow update speed. Of course it does. It has to be like that. So this is one memory enabled, but we can enable all three memories and then have my live. So there is actually 4 sets of memories, and each of the memory sets can have the 2 channels. So that will be 8 curves, as you see here, right? So if I turn off channel 2, now I have channel 1, right? So if I store by using the store here, only one channel is enabled, so only one channel is stored, and that will be my 4 different curves then. But of course, if I enable the other channel and do the store, then it's doing like that, completely automatic. It is really a nice digital scope, and it's so fun to play with. And also I like there's another thing I really want to show you. This little springy contact we have right here, really close to each of the input B and C connectors, like that. So if you see, there's a tiny little springy contact here that's measuring the resistance in this outer ring. So this is the connector for an original Philips probe. So there's a built-in resistor in here that tells the scope to switch range. And the Philips original probe, they use 2.2 kilo ohms for the resistor change. So let's see if that works when I put it in like that. Did you see that now it changes the readout here, and it's probably also changing the readout here in the B. Let's take it out and in. Yes, exactly. So now it goes 10 volts per division instead of 1 volt per division. So now your readout is correct. A previous owner of this oscilloscope probably was really smart, because he wanted to use other probes. So this little piece of circuit board here, there's a contact between the top and the bottom layer, and there's a mill out here, so it fits here. Oops. So the idea is this piece goes here, and then nothing happens, right? But if you take a Teardown scope probe, they got this springy connector here. And the fun thing is that Teardown probes, at least this model, uses 11 kilo ohm to tell a Teardown scopes that this is a 10-to-1 probe. So let's see what happens. Nothing happens. And it's because it's the wrong resistor value. But it was supposed to work. Maybe if you have another 10-to-1 probe with the 2.2 kilo ohm, of course it's going to work. That is what I think this was for. It just don't work with the Teardown probes that I have, and I'm sorry I don't have any other brands of resistors. But at least it was fun the way that they made this little ring here, right? Let's test the frequency response. So this is 10 megahertz, and my input is 2 volts per division. I have adjusted the input level here to be exactly, as you can see here, in the middle of the max allowed range. So that is full input. So that was 10 megahertz. I've of course got my feed through load here for my cable and generator and all that. So that is 20, 30, 40, 50, and 60. Look at that. Oops. Okay, let's go back. That is not good. Oops. Hello. Okay, here you are. Are you back again? Oh, we have a little problem with the scope at the moment. It is dying on me, is it? So there's something to do with not tricking. That. Okay, so let's go back to 60 megahertz, 70, 80, 90, 100. Remember, the front end is 125 megahertz, so 110 and 120, and it's gonna go like that, 110 again. So there's a very good restore filter here that is restoring the signal, so that is 60 megahertz. So all that seems to be working. Can we even? Yes, we can. Cool. I don't know if you have noticed that I got 2 of these scopes in for service. One is in a little bit sad condition. As you can see, the front shadow here is missing. And I don't know if you remember my previous Philips video where I designed and 3D printed a screen shadow for the other model. That one fits perfectly on this model, so I'll be able to save it. How cool is that? And the top one here that is working really good is missing its feet. So I don't know if you have seen this, what I got over here, but I made new feet. So they're gonna go on the top one. So now that one is completely fine and good to go. And then we'll start to play with the bottom one, and that is full of funny things, and that is what we want to open and play around with inside. Oh yeah, by the way, the original feet, look at that. They got a little rubber, see, and this little rubber feet part here of it is just completely dissolved. It turned itself into splat or chewing gum or some. Yeah, it's very close to chewing gum, the feel of this. And of course one of them broke. I put it on the floor and then I lifted the scope and this one was sitting on the floor. It's terrible. So yeah, they gotta go. You can see it's completely dissolved. And when you touch it, it feels like touching old chewing gum. So that is just gross. You're gonna screw up your floor. But that's quite easy just to unscrew this and put the screw back in, and then the washer will go all the way in here. See, there's even a little groove for the washer and the screw, and then it'll still be able to stand on the floor without scratching the floor with the screw head. So here is how it looks. My 3D designed feet for the Philips scope. Let's go 3D print. So that's the original one, and that's the 3D printed one, and of course it fits. This is the first prototype, and I had to remove a tiny little bit of material here because the metal down here has a little bend. So this is of course compensated for in the new design that I'm sharing for free on Thingiverse. It even fits like that. So I don't like the cable grooves for the wire winding up and holding like that, because when you do this you bend the cable the same place and again, and it's really not good for the cable. So and it's also, if you would do this design in a 3D printed part, you can imagine it would be a terrible job to 3D print it. I could maybe put it like that and 3D print it quite all right, but it will make the part really weak in its design when it's 3D printed. I want as much material to make it really nice and strong. And I printed this in PETG, running at low speed and at a little bit over temperature, so that the layer to layer melt will be better. So it's really tough. I also found some extra screws with a little bit extra large head and the right washers. So they're 55 millimeters long, exactly like the original screws. So yeah, now I can restore the other scope with the missing feet, because it's driving me nuts not to be able to put a scope on the floor like that. It's really terrible how much they occupy of space if they're not standing upright when you're not using them. So now I'm trying to play a little bit with the other scope. Let's see if I can get a little bit more intensity here. So this is a roll mode. It's really cool. This is a 1 hertz signal, and it is going nice and steady like that. We can of course change the sweep time and all that kind of stuff. So when it's been running for a little while, it kind of stops like that, and then it shows that it's not running anymore. That is a little bit funny with the roll mode. You would expect that you can just hit run here and make it go again, but no, you need to clear your write and then start again. So I think that is a little bit weird, isn't it? We're missing a bulb up here in the time base, so that is a little bit funny. You can also go out of roll mode and going into the normal mode. We have a little bit of problems with this scope when it comes to input range affected by the different sweeps, different type of settings with the time base. As you can see here, it is now truncated, and then we can change the time base. See, slow time base like that, and then you will get your signal. You can also run faster and then crank up our input signal. So this is 10 hertz, and then we should be able to get some signals here like that, right? So this is what I wanted to show. This is a 1 kilohertz signal, and now the signal is truncated like that. So then this is our input range. Can be almost 3 divisions, 2.5 or something like that, right? So let's just try and keep it in the middle here, and then you see the time base here. Oops, see there's a new problem, and this goes from 0.5, and that is exactly when the time base is changing the behavior of its modes. It's activating this input sampler, and then it goes a little bit in and out of that system. So there's definitely a problem. I've been trimming around in the input sampler because it is an analog sampler, and I really made it work quite well. Let's go up to 10 kilohertz, and then we can crank up here. See, it is still almost the same, right? We can go faster and faster. So that is 10 kilohertz. Let's crank it up to 100 kilohertz. And then we just continue here. And it goes all the way up. That is 1 megahertz. Oops, see? And here is the problem. Again, now we change modes again, and the input sampler is really, really bad. But when I go to the next step, it is good again. So there's definitely something to do with time base and clocks and levels in and out of the input sampler that is affecting how this scope works. And I can actually trim it to be good in this particular setting, and then it will be bad in all the others. So I think I will leave it as it is right now, because I think this is the best of the bad that I can do. But there is definitely something here. And here is the bottom side. As you see, the 2 inputs go straight into here. The analog front end, attenuators and all that kind of stuff is in here. And that will be trick and all that stuff. And of course the triggering takes a little bit of time, and we want to be able to grab the first or the leading edge of a fast pulse. So here is the joint analog. That one is a delay line. So it goes down here and comes up here. So this is the merged vertical, and then it's amplified and sent to analog to digital converters on the other side. I'll of course show you guys this in a minute. There's another little funny thing here in this. This is of course the intensity and power on. Look at that. So somebody didn't figure out the size or the accurate position. So now they had to mill this thinner right here, so we got room for the transistors and this coax connector. That's a little sweet thing to notice. Yes, and of course the power supply, voltage adjustments and everything in here. But again, this power supply was serviced, so I'm not going to poke around too much with that one. Of course, you want to see the analog front end input here. Look at that. We go. So this is the AC-DC capacitor, of course. And then the attenuator is, of course, made with read relays, because everything in this one is software controllable. It looks like the attenuators and everything here goes to handle stuff directly, but no, it goes via relays. And that is a very good way to do it, by the way. And look at the channel to channel isolation. There's a wall between here, and it's just really well built. A lot of trimmers for the analog front end. And DC filters. This is typical Philips. See, they're using the same holders for filters. See, they put in ferrite. And they're using exactly the same mechanical part for their reed relays. That's a little bit cute. And this is the input sampler I'm talking about. This one is running at 125 megahertz when it's running fastest. And clocks comes from the time base and is amplified here. So there's a positive and a negative phase of the clock. And it goes into this P2CCD chip. It's an analog shift register sampler that handles the input samplings. And that chip is mounted on the back side of this PCB, so it's cooled by this aluminium profile. And I believe that is where we have our problems. Other than that, this scope is really a nice modern design with plug-in boards for all the different digital circuits. That will be the numbers of the different circuit boards. Start with number 4, and then see, we skip 11, and then number 14 is not mounted, and then we go to number 20. So that will be the numbers from the documentation, and the different modules. That will be the CPU module, RAM, buffer, AD converter, acquisition, and CCD timing logic, time base, and this is delay trick. This is the IEC. This is actually an external data interface, and that will be the amplifiers, the final amplifiers for deflection. We're going to look a little bit more on the different modules later. And the power supply is already serviced in this module, in this power supply, so I don't really expect to talk so much about the power supply. There is already so much documentation about this power supply online, and yeah, there's a reefer capacitor you need to service, and there is a main input filter that's always shorting. So those two things you definitely want to address first of all. We got some really nice filters right here for all the different DC rails, and the high voltage is coming out of this transformer that goes to the tripler, and that goes of course to the anode of the tube. Let's look a little bit on the different modules. So this is the CPU module, and of course the 8085 CPU, the two EEPROMs, and here we got the two EEPROM upgrade. One of them is the software you need for the plugin for the expansion port, and we got two of the RAM chips, 4-bit in each, 256 bytes is what we got here of RAM, so it's not a lot, right? So then the next is RAM and DACs. So those two are 8-bit DACs for X and Y. In the playback mode, it's playing back to the screen using those two DACs. Again, RAM is 4-bit in each chip, so that will be the live display is here, and then storage 1, 2, and 3. So this is actually 1 kilobyte on this board. Isn't that just amazing? So this is the A8 analog digital converter. So it's using a Brown converter. It's actually a 12-bit parallel output SAR converter, but they're using it in 9-bit mode so they can just clock it faster. It's originally designed for 12 bits, 800 kilohertz maximum. And on this board we also have maximum and minimum overflow handling, and this is why we see the curve blink when we have reached overflow conditions. So it's all done here. Beautiful AD converter here. Oh yeah, the other module here we skipped, that is the buffer module for the AD converter, but this is just not interesting. It's just a shift register and a DA as well. So not a lot of interesting stuff going on there. So here is A10, the CCD logic. This one is driving the different voltages and all the different timings to the P2 CCD sample, analog sample registers. So that is why you have all those different trimmers. That will be all the analog setups, because it is analog storage. So it's very, very complicated what they're doing here. But definitely they're storing very high speed analog pulses into 2 times 128 bits. And then it will be slowly clocked into the AD converter. So that is why you can go this fast. It's a very complicated way they've done this, by the way. I don't pull this card out the entire way because it's full of some coax cables, and I don't want to misplace the different connectors again. They are indeed color coded, as you can see, but here, for example, there's another one, so it is easy to screw this up. And it is, of course, nicely shielded, because this is also analog. Here is the time base module called A12. It generates all the frequencies we need depending on the different sweep time settings. You'll see this table that shows all the different clock frequency outputs used for different parts of the unit. Here is A13, the delay trig module. Consists of down counter delay counting, and there's also I believe this counting generates a ramp, and that ramps those are fed to this DA converter, and then that voltage is used for the trig delay. It's a little bit weird way to do it, but I think this is how they do it. Some of the parts here, they're ECL, super fast parts. Well, that is of course needed because this thing can trigger on very fast signals. Here is A20, the final X and Y amplifiers for deflection, of course. Got a little bit high-speed amplifier here, but the rest is just this little tiny transistor set here driving the deflation. And of course this is possible because this scopes playback the screen at a quite slow speed. So that means the CRT is kind of slow speed and all this is slow speed, and it's displaying the same speed no matter what kind of input time base settings. So you get the same nice brightness and yeah, all that is really, really nice. I've been fighting quite a long time with XY mode, and it seems like a XY mode is really, really difficult to use on this scope. Look at the kind of ridiculously bad picture I got here. It's doing all those different dots, and it's just absolutely useless. And I can tell you, it's blinking and blinking. I've turned down this the light so much here, and I'm trying different modes with the trigger and auto trigger, and I need to have auto trigger on external to even get a picture. See, if I take auto trigger and use AC or DC, and if I turn this, I get no response, and then what the heck is going on here? It's just absolutely useless. I don't know. Funny. But anyway, I just want to say thank you very much for watching. It was fun playing with this scope, and I think it is more or less back to a very usable state now.